those. They are becoming neighbors as well. And you can, if you're simplifying the map, combine them as well. So we did one example where we combined the corners into one function, B naught, D naught. But if we have, for examples, the ones here, then you can combine these two as well. Or if you would have ones here, then you could combine these ones as well. Here we have zeros, so therefore we are not combining, but if you would have ones, we can combine them as well. So maybe you're trying yourself to understand what is happening if you're rolling that. Maybe you're just taking a piece of paper. Let me just pick one. A square one. And if you are now rolling that, then you will see that the two long sides, I don't know if you can see, are neighbors as well. And if you're rolling the other way around, then the other two long sides are neighbors. And if you're forming that to a donut, which is maybe not working with a piece of paper, but if you have something else, then they would be neighbors as well. And there was no rule how you're rolling this K-map. So here there was an animation which is working in the PDF, but not on my machine here. And it's also linked. Just copy that. Okay. Then let's continue with our tutorial. Did you try to solve the remaining problems of that one? I guess we ended up at that one during our last session. And we yeah, that was ours. And we saw that this will be the results of the other patterns. Maybe we are doing two further patterns from that problem. So one would be, let me just look into, let's do B and C in addition. So the pattern given for B is 1 0 1 0 0. 4 times 0, no, 3 times 1 0 0 1 1 0. And 0 0 1 1 0 0. And C maybe is 0 1 1 1 0 1. 0 0 0 1 1 0. And 4 times 0. And 0 1 0 1 0 0. And our original table was that one. So please try again by your own to decode these bit patterns into the text. Let's say for 10 minutes, and then we are looking into that together. So someone posted the correct result in the chat. The others, do you have a result as well? And are you aware how this is working? Or do you have issues? C. So someone wrote if I can explain C, which means you're fine with B? Or? Okay. So if you're fine with B, then let me just note the result. It is fed. And now we are looking into C. And the first pattern that we have there is 0, 1, 1, 1, 0, 1. And you are not finding the pattern in the corresponding table. So there is no 0, 1, 1, 1, 0, 1. What you are doing now is you are checking the Hamming distance of the 0, 1, 1, 1, 0, 1 to all the other symbols there. So if you are comparing to A, the Hamming distance is 4. If you are comparing to B, then the Hamming distance is 1, 2. If you are comparing to C, the Hamming distance is where we are, 1, 2, 3. If you are comparing to D, the Hamming distance is 1. Compared to E, the Hamming distance is 1, 2, 3, 4, 5. Compared to F, it is 1, 2, 3, 4. Compared to G, the Hamming distance is 1, 2. And compared to H, the Hamming distance is 1, 2, 3, 4. So the shortest Hamming distance that we have is the one with D, because here the Hamming distance is 1. So let's note here below the value for D, 0, 1, 1, 1, 0, 0. So here the Hamming distance is 1. It's just different on that bit. And therefore, that's the lowest Hamming distance that we can find. And therefore, we are replacing the obviously wrong bit pattern by a D. Then the next one, 0, 0, 0, 1, 1, 0. We are also not finding here. And we are again comparing. And the shortest Hamming distance that we will find is the one to E, because for E we have 1, 0, 0, 1, 1, 0. And here the difference is in the first bit. So again here the Hamming distance is 1. And therefore we are replacing that by an E. Then for A, it is obvious. It is the right bit pattern. And then we have 0, 1, 0, 1, 0, 0. And again, there is no symbol or there is no bit pattern which is represented, or no symbol which is represented by the bit pattern. So we are again replacing by the bit pattern with the lowest Hamming distance to our original bit pattern. And that's D in this case, because for D we have 0, 1, 1, 1, 0, 0. And the shortest Hamming distance that we have is that one. So it is different in that position. So the Hamming distance here is again 1. And by that, we are replacing by a D as well. Is that clear?
Sorry, so how do you check the Hamming distance?
I'm comparing with the original bit pattern. So let's maybe do that once more. Let me just. And let's do that for each bit pattern if necessary. So let's again do with C, okay? So in C, what we received was 0, 1, 1, 1, 0, 1. Then 0, 0, 0, 1, 1, 0. Then 4 times 6 times 0. And 0, 1, 0, 1, 0, 0. Now I'm starting with the first pattern that we have, 0, and comparing with each possible bit pattern. And now let's just mark where the bit patterns are different. So here, the second, third, and fourth bit is different, and the last bit is different. So the Hamming distance here is 4. Clear?
Yes, it's good, yeah.
Then for the next one, the first is the same, the second is different, the third is the same, the fourth is the same, that one is different again. So here we have a Hamming distance of 2. Then for the next one, so 0, 1, then 0, 0. So the Hamming distance here is 3. Then 0, 1, 1, 1, 0, 1. It's just the last one. My Hamming distance is 1. Then we have 0, so here the Hamming distance is 5. Then for the next, the first bit pattern is different, the second is different, the third is the same, the fourth is different, and the last two are the same. So the Hamming distance is 3. For the next bit pattern, 1, 1, 1, 0, 1, 1, 0, 1. So here the Hamming distance is 2. And for the last one, so 0, 1, 1, and then 1, 0, 1. So here the Hamming distance is also 4. And now I'm searching for the bit pattern with the smallest Hamming distance. That's that one here. And I'm replacing my received bit pattern by the one with the smallest Hamming distance. So in this case, 0, 1, 1, 1, 0, 0, and that's a D. So with an Hamming distance of 3, So this bit pattern has, the original bit pattern has a Hamming distance of at least 3. And with a Hamming distance of at least 3, I can detect 2 errors and correct 1.
Sir, is it possible in a scenario where they like for the second time we are getting the same having distance?
Sorry for?
Like for example, having distance it has to be the lowest, right?
Yes.
But is there a possible scenario in which the having distance is same for two bit patterns?
Yes. Then you have 2 errors.
Okay.
So there is a scenario, and if you have the same Hamming distance for 2, and these are the smallest, then you have 2 errors and you can't correct. So with the Hamming distance, you can detect 2 errors, but correct only 1 with a Hamming distance of 3.
With the having distance of 3, you said?
With a Hamming distance of 3, you can detect 2 errors and correct 1. You can't correct
Okay.
both errors with a Hamming distance of 3. Okay. So, and then you are redoing that for each pattern. And that's it. Okay, then let's continue a bit. Just 1 second. With some tutorials on Boolean algebra. So here you see a logic circuit with 3 inputs and an output. And you should find out which bit patterns at the input are causing a true signal at the output. So please try that by your own for 10 minutes, and then we are looking into that together. So just the first problem, 1 here. So let's may start with the first problem, or do you still need some time for the first one? Okay, then let's start to look in the first one. Let me just redraw. Or first of all, what kind of element do we have here?
AND gate
An AND gate, right? And that one?
or gate.
No?
XOR gate.
XOR. That's an XOR, right? So that's an XOR. Here we have an AND. So I will may redraw that on an additional slide.